Hi everyone, a very good afternoon. Before we begin this talk, I just want to thank the entire Scala UA organizing committee. I think they have done a wonderful job given the circumstances we are in of organizing this conference virtually. And a big thanks to all of us who are here in this talk.
Thank you very much. We are more than glad that you are here today. Thank you.
Yeah, so about me first, my name is Ayush Mittal. I work for HCL Technologies in Amsterdam. HCL provides digital services to its customers. Currently, I'm working on a contact center application, which is digital. So when people generally think about contact centers or call centers, they tend to think about hardware, phones, but this is a digital contact center. We receive calls on phone, we dial calls on phones using software applications. In my spare time, I also do some open source programming. You can check me out on GitHub at AyushWorks. This is my GitHub repo link. So let's get started. What do we want to take out of this talk? What are the key takeaways that we want to have at the end of this talk? We should understand what effects are and what do we mean by effects in Scala and in functional programming. We should be able to gain insights and have a vision of why we need effects in a language like Scala. We should also be able to clearly understand what are side effects and how side effects are different from effects. We should also understand why, as a programmer, we should stay away from side effects and we should avoid them in our code bases. Finally, when we have gained this much picture, we will be able to understand the core concepts and the ideas behind effect libraries such as CATS effects or Zio. This is our goal for this talk, so let's get started. Effects. What are effects in Scala? Let's look at some examples. Any Scala programmer in his work must have come across the option type. Option models the effect of optionality. We have a scenario where a value could be present or it could be absent, like fetching items from a database. Given an ID, I want to fetch the customer, but the ID might be present or not present in the database. How do I represent this to my consumers? How do I tell them that it might be absent also? I use an option effect. Another very popular effect in Scala is the either effect. It models the effect of one of two. You could have multiple possible outcomes from your program and you want to represent that in the result type of your program. So you use either. A very simple example, you're trying to verify an email ID. If the email ID is correct or wrong, you can return an either type so that the consumers of your API understand that the verification might fail with an error or it might succeed, and in which case we don't return anything. It's a unit. List is also an effect. It models the effect of having 0, 1, or more than one elements in a collection. An example, I want to fetch a list of agents from my database who match a particular skill. Now I might have one agent, I might have more than one agent, or I might have no agent matching the skill. A list is a perfect way of representing such a result type. There are many other effects in Scala like reader, writer, try, but these are the pretty basics ones that most of us have already seen. But what do we like about these effects apart from what they represent? What is the benefit of these effects? The benefit of these effects comes in terms of composition. The way we write code, the way we write applications is that we have smaller programs. We write small code that we understand. We write testable small units of code, and then we compose them to build larger applications. Any application that is built in such a way is always scalable is always easy to refactor. The same holds for effects also. Effects are composable. Let's look at an example of what I mean by this. Let's suppose we are trying to build an application that calls our customers and informs them about a change in our branch timings. We want to inform them about a new marketing scheme. We want to build an application that calls the customers. So to build such an application, we need smaller recipes. We need smaller chunks of code that we can combine to form this. Let's look at those smaller chunks of code first. Here is one such recipe that given a customer ID, I can fetch the customer phone number. Now the business logic dictates that the customer ID might not be present with us. We might not have this customer in our systems. So the result type of this particular program is an either, with the left indicating that the customer is not available with us and the right indicating the presence of a phone number. One more recipe to build this application is actually dialing the customer. Given a phone number, we create an actual call, and this call object can represent an instance of call between our application and the customer's mobile device. But this function could also fail if the number is not valid or if there are network issues in the trunking. So now given these two recipes, how do we compose a bigger application? Always the idea in functional languages is that we use the output of one function as the input to the other function. But if you look here, the output here is an either and the input here is a string. Now, how do you compose them? Effects in Scala by their very nature are monadic, and by monadic, I mean they have operations that allow us to compose them. We have operations like flat map and map, and in this case, we can use flat map. So given a customer ID, we first fetch his phone number. If we get a phone number, we dial the customer. And flat map takes care of short circuiting the code whenever an error occurs. If there's an error in getting the phone number, the dial customer is not called at all. So we get some inbuilt short circuiting of error handling as well. This flat map can also be represented in its sugar syntax way, which is using the for comprehension, and it looks very easy to the eye also. So this is another way of composing our bigger end software. So what I wanted to say was that the effects in Scala are good because they compose. They allow us to build larger applications from smaller ones. Having said that, let's move on to a different topic now. Side effects. Now, let's understand what side effects are and how we can relate side effects to pure functions. Any function that has side effects generally is impure, but this definition varies across different groups of people. If you ask certain developer what a pure function is, they will probably come up with some answers like immutable code. If a function has no mutating logic, then it is probably a pure function. Some might say that if a function produces same output for the same input, it is a pure function. That is also a valid accepted definition sometimes. Some developers might say that if there is no use of external variables, then our function is a pure function. But this is not the complete picture. There are certain more aspects that we need to look into. Let's take an example and understand why this might not be the right definitions of a pure functions and what we might be missing. Let's look an example of a function now and see whether we can say by looking at it, it's pure or not. So here is a very simple function. We are trying to check if the function is, if the number that is being passed to us is divisible by 2. So the business logic is pretty simple. If the number modulus 2 is 0, yeah, it is divisible by 2. But there is also a function in between this call which says increment counter. Now, unless the function name is wrong, increment counter must be incrementing some sort of counter in our application. It might be performing a database update, incrementing counter there. It could be incrementing counter in a Kafka topic. It could be doing anything. That's what it looks like. Now, is this function pure? Well, if you look at our definition, this function produces the same output for the same input. And to produce that output, it does not use any external variables. So what can we say about this? Is this pure? That's debatable. Let's look at another function now. Again, we want to check if a number is divisible by 2. However, this time we have a if-else condition. We say that if it's a weekday, then do the normal check. Check if the number is divisible by 2. But if it's not a weekday, then throw a runtime exception. Well, this function does not interact with any external variables. It does not have any mutation. Is this pure? What can we say about this? So there are no perfect answers by looking at these things, what a pure function is and what a impure function is. And maybe we need to discuss the concept of referential transparency. Now, what is referential transparency? Let's look at the definition first. An expression is referentially transparent if it can be replaced by its value without changing the program's behavior. That is a simple definition. What does it mean? Let's take an example. We have a val x, which is defined as 5 plus 4. Now, throughout my program, I can replace the value x with 5 plus 4, and the program output will not change at all. So I can confidently say that this expression is referentially transparent. Now, there is a lot of debate in the community on whether every referentially transparent function is pure or is it the same thing. Let's not go into that debate. What we can agree for sure is that referential transparency does not guarantee purity, but all pure functions are necessarily referentially transparent. If your function is not referentially transparent, it cannot be a pure function. So the bare minimum necessity to be a pure function is referential transparency. And for the remainder of this talk, we will assume that when we say a pure function, we just mean it to be a referentially transparent function. Let's keep it simple for this discussion. Now, why do we think we need referential transparency in our code? Why is it important to have referential transparency? Referential transparency makes it easier to read and understand your code. And any developer who has worked on a commercial application knows the importance of having a code that is easy to read. 80% of your time we will be spending in our code bases reading the code rather than writing. So any application that has to scale, that has to adapt to new changes, that is worthy of refactoring if required, has to be easy on the eye. It has to be easy to understand. That easiness comes with referential transparency. That easiness comes with writing functions that are simple and pure. So referential transparency gives us this advantage that we get to focus on business logic. If we want to understand the code, we follow the trail of the business logic rather than looking at what the function does inside. By looking at the function signature itself, we get to know what this function might be doing, and nothing more than that is required. Functions that are referentially transparent are super easy to test because they generally do not do any side effects. They have local reasoning. I just mentioned that by looking at the definition of a function, you can understand what the function will do and what it will for sure not do. And also refactoring a code base that has pure functions is super easy. So Because of these reasons, it is very important that we get a liking to referential transparency. We understand why we need the referential transparency in our code bases. The problem with side effects is that side effects break referential transparency. A code that has side effects cannot be a referentially transparent code. And we can look at an example. We just saw our function which checks if a number is divisible by 2, and there was a weird call inside that function to increment counter. And we were wondering if this is referentially transparent or pure or not. Let's look at the usage of this function. Suppose we build a software where we have two input numbers, and the software logic is that if both numbers are divisible by 2 or not. We check if both are divisible by 2. If both are divisible, we return true. Otherwise, we return false. It's a logical AND. This looks like a good software, but as usual, there are code reviews. We try to do optimizations. Here is one optimization on this code. If both the numbers are same, then we don't need to call the function underlying twice. We just can call it once with any one of the parameters, and they're both same, so the result will be same. So if you look at software 1 and software 2 alone, you would say that yeah, this seems to be a good refactoring. This seems to be a good improvement. But what you might miss is a subtle bug in the software version 2. A bug in the sense that now the software behaves differently. Why does it behave differently? Because if I call it with the same parameters, the increment counter is not called twice, it is only called once now. So even though the output is same, the end state of our application, which we should worry about when writing out code, we should worry about how we leave the end state in. The end state is different for software 1 and software 2. Software 2 does not increment counter twice while software 1 does. It is not important which of the versions is right, but the important fact is they do not behave in the same way. And this is caused because of the logic inside the function to increment counter. So this is a very simple example to understand why we should avoid programs like this, which are not referentially transparent. So we saw a function with side effects, and now look at some of the very common example of side effects in our code. We will for sure have side effects in our code. They are unavoidable. Even though we don't want them, they are there in our code bases. Database interactions, saving item to a database, deleting an item from database. This is a side effect. Logging, reading to a file, writing to a file. This is a side effect. Reading from console or writing to console. This is a side effect. An HTTP request in your application is an example of side effect. Can we create a commercial product which does not have any of them? I doubt that. I think any bare minimum production worthy application must have one of these effects for sure. So what have we learned at this half? We have learned that side effects are not good because they break referential transparency, and we understood why we need referential transparency. We understood that referential transparency and pure functions are very good. They help us keep our code base clean, easy to read, easy on the eyes, and easy to understand. We also looked at some side effects, and we understood that they are unavoidable. You cannot have a code base without side effects. So here's a problem then. Well, with a functional language like Scala, the answer always lies in creating data types, creating abstract types to comprehend the problem that you have at hand. So we discussed about effects. We saw effects like option, try, either. Maybe we could create an effect type to model side effects. We could create an effect type that describes our side effects. What rules or what requirements rules do we have from this effect type? Our new effect type must be a wrapper for side effects. We should be able to wrap any side effect like writing to database, reading from a file, writing from a file. We should be able to wrap such side effecting code in our new effect type. Our new effect type will be a description of these side effects. We should be able to suspend synchronous or asynchronous code blocks in our new effect types. And the new effect type only describes our side effects, does not run them. The actual execution of side effects happen at the very end of the program, only when we intend to. So basically, we are saying that we create a new effect type to wrap our side effects, and we run the side effects only at the end of our code. We move all the impure code to the end of our application logic. There is, looking at these rules, existing Scala type that comes to mind is futures, which are very popular for wrapping code blocks and doing parallelism in Scala. So can we use futures for referential transparent code? Can we have future as a candidate? Unfortunately, futures are not an ideal candidate for writing pure functions. And here is a famous example from the Rob Norris tweet, Reddit post, I think. Yeah. So here is a program. I am creating a future of a random UUID, and then I'm using that future, and I have my program. When this program finishes, I have two UUIDs which are exactly the same. So future is eager. As soon as val future is declared, it starts running. The value is ready, and the same value is assigned to first and second. Now, if future was referentially transparent, I should be able to inline that call to future. I should be able to say the following. Instead of assigning that variable, I can just inline the call to the future. But as soon as I do that, the program produces a completely different output. The two UUIDs are not same now, they are different. And this is the best example to prove that futures are not referentially transparent. They are eager in nature and cannot be used for our use case. So back to our original problem. How do we create a new type? Let's call it the effect API. We will represent this type using F, which is spelled as EFF, and F of A describes a side effect that when executed produces a value of type A. We want our effect type A to be referentially transparent, and we want it to separate pure code from impure code. So requirements of this. What do we need from the interface? The interface should allow you to wrap impure expressions into an F type. Given an impure expression like writing to database or reading from the console or a HTTP request, you should be able to wrap such impure code blocks into an F type. You should be able to create an F of that type. And that is the requirement from the interface that we expose, the FFI. We saw why we like effects in Scala because they compose, and we have the same requirement for our new F type also. We want our effect type to have combinators. We want them to support operations like flat map so that we can build larger programs from smaller applications. And also we want runners. We actually do want to produce a valuable product at the end. So we want to have a runner that runs the side effects, but runs them only when we want. And we run them at the end of the world, or to say at the edge of our code boundaries. So these are the three basic requirements for our effect API. Now, there are other things also that we should consider, that it should do error handling, it should support concurrency, asynchronicity, parallelism. But for the sake of simplicity, let's assume that we are only focusing on a very simple effect. We want it to be pure, referentially transparent. We have a synchronous foreign function interface. You can supply a synchronous block of code and it will wrap that in an effect. And we want sequential composition. We want operations like map and flat map, which is very much required. So now let's think about how you can design such a type in Scala. Uh, let's look at the API once again. So this is our interface. This is our foreign function interface. There is a method delay. This takes a synchronous block of code and produces an f of a. This is how users of our effect type can wrap side effects into an f. Apart from the FFI, we have combinators where we have pure, flat map, and map. These are pretty similar to what we have in regular Scala effects like option or either. A flat map has an effect and a function from the output of that effect to another effect. A map has an effect and a function from the output of that effect to another value b. And pure just takes a pure value and produces an effect of our type. So we have the FFI, we have the combinators, and we have the runners, which is the side effecting code. Here we actually take an effect of A, execute the side effect, and return the value A. So now let's put our design hats and think about how do we design such an effect type. What can we think about it? So in Scala, the recipe for designing such types is pretty simple. That is how options or ethers are designed. We will use algebraic data types to design our domain models, and we will use an interpreter pattern to run the effects. So in algebraic data types, we basically use case classes to represent our domain models, and that is what we'll do. So we'll have some data types. Obviously, there is the root, the starting trait, the f, which is an effect of A. Now we'll have some data types that represent what an effect can be. It can be a flat map, which takes an f and a function from the output of that effect to another effect. Then we have pure, which takes a pure value and creates an effect. And finally, the most important one is the delay type. Now, this is where the magic of purity and referential transparency happens. Delay takes a function from unit to A. This function is basically where the suspension of side effects happen. We take any side effect that can return any type of value and we suspend it using the delay type. When we have an instance of delay in our hands, the side effect is described, but it is not actually running. It is only a description of the side effect. And this is a very important concept. We only execute side effects when we want them to. So the delay type here is providing us with referential transparency and purity. So this is our data types that we need. And if we look at the entire picture, we have our trait f of a, which has combinators, flat map and map. They are pretty straightforward. We just saw the data types. We have a flat map data type. We have a pure data type. We have a delay data type. Delay is very crucial. It takes a function from unit to A, and this is where the side effects get suspended. And of course, we have a interface. We are telling our consumers to call the delay method to suspend any side effect that they want to. We also have a method pure that basically takes a pure value and creates an f of a. So this is how our effect type f looks like. Now, how do we create programs using this class? How do we describe programs? Let's look at an example. Suppose we want to create an application which is an echo application. It basically reads data from the console and writes the data back. We agreed that reading from console and writing to console is a side effect. So we must use the delay method to wrap those side effects. So let's see how we do that. Here it goes. We have a method read from console. In an impure world, this method will only be doing scala.stdin.readline, but we want to create pure functions. So we have wrapped the side effect, which is the readline operation here, into a delay. When we have an instance of this type, it only describes the operation of reading from the console. It does not actually start reading from the console. It only describes that operation. Similarly, we have an effect that describes the side effect of writing to console. Writing to console is using println. We have wrapped that side effect in a delay. So when we get this effect, it only describes the side effect of writing to console. It does not actually do anything. And here is our program. We read from the console. We use the flat map combinator, which takes the input from that effect type, which is a string, and prints the string to the console, which is again an effect. So this is how we have built a larger program from two small programs. Now, just for clarity, if you look at the program, what does it mean to have a program at hand? What is it composed of? So we saw that there are three types: flat map, pure, and delay. And let's understand in the terms of these three types what a program is. So program is a type of a flat map. Inside flat map, we know that there is a effect type and a function that goes from that effect to another effect. The effect type inside the flat map is a delay, which represents a side effect of reading from the console. The function is here. It basically takes whatever was read from the console and prints it to the console. So a program that we see here is basically a description of all the side effects that our software will do. It does not actually start doing any side effects, it just describes them. Also, for the sweet syntax sugar, we see here that we can also write program in this way using the for comprehension. Read from console, get the input, write to console using the input, and we get the out. And the final output is the out. So this is how you will create programs using your new effect types. And we have seen the importance of the data types here, how they are used to compose these three things. Now, once we have our program ready, the next step is to actually run the program. So how do we, given an effect, how do we execute the effect? Running the effect. So we agreed that we'll follow the interpreter pattern to run the program. And what interpreter pattern means is that we look at the description of the effect, and based on the description, whether it's a flat map, whether it's a pure, or whether it's a delay, we run the instruction. So let's look at a very naive and a very simple way of running an effect. We have an f of a. We are using the interpreter pattern here to run this effect. We do a match on the effect type. If it's a pure, yeah, then we have the value ready with us. We just return that type. If it's a flat map from an effect and a function that takes that effect and returns another effect, then we first have to execute this effect. So there is the execution of the first effect, then the call to the function with the value of this effect. It gives a new effect, and then we run the entire effect again. This is how you would instruct your code to run a flat map type. What if we have a delay type? Delay type means now we are ready to actually do the side effects, and this is where side effects happen. This could be, in our case, read from console or write from console. So basically, we perform the side effect, we wrap that operation in a pure, and we run. But uh, this particular piece of code, this run implementation suffers from the problem that it is recursive in nature, but it is not tail recursive. It can lead to stack overflow errors, and it will happen pretty soon. So we now need to come up with an implementation of this run, which is stack safe. And by stack safe, we mean it has tail recursiveness. Now, to understand this version of the effect run, we must keep in mind what a flat map is. A flat map has an effect. It has a function that takes the output of that effect and produces another effect. Now look at the tail recursive implementation of this run. And you might notice that in the method loop, we have a effect of type any, and uh, being Scala programmers, we might be wary of what the any type is and what is it doing here. Well, any type indicates is strange, but we are guaranteed type correctness. We don't need to worry about type safety here. Because we have composed our programs using our data types of delay, flat map, and pure, we are guaranteed type safety. The tree structure that has been built is type safe. We don't need to worry about type safety issues with our run program. It would be really complex to keep track of all the types because we might have thousands of flat maps. So it might be difficult to keep track of an int to a string and a string to a boolean and a boolean to a list and so on and so forth. So we use the any type here. But the guarantee that our program will eventually return an A is inbuilt because of the data structures we have used, because of our data types, the ADTs that we have described. Now, the loop method basically has a current effect F, and it has a stack of the pending flat maps it has to execute. Once we start pattern matching, we first see what is the current effect type. If it's a flat map, that means we have to keep on looping. We have an effect and we have a function that takes that effect and produces another effect, but we cannot run this function yet. We need the side effect value from this F before we can call the function. So what we do is we put this function in the stack and we loop, we go forward with our execution. Let's look at what happens when we find a delay node. When we see a delay, it is time to execute the side effects. So here we are executing the side effects. We are actually doing operations which could be print line, read from a file, etc., etc. And they could throw exceptions, and in our case, if they throw exceptions, our run will also throw the exception. But we are not worried about exceptions. We just want a simple effect type for now. So if we have a delay node, we execute the side effect. Once we have the value ready, we call the loop again. We create a new F type by calling the pure, and we continue with the same stack that we had. What if we find a pure node type? If we see pure, then there are two possible options. If the stack is empty, that means we have reached the end of our programs. All the flat maps have all eventually finished and we are at the end now. Now we can actually return this variable. We are done with the execution of a program. However, if there is some operation that is pending that takes a variable and creates another effect type, then we need to execute this operation from the stack. So if there is, we pop out the first operation from the stack. We execute that operation because we have the value now, and we call loop again with the new effect type that is created. And the stack now consists of only the remaining portion of what has been left after we popped. So this is a pretty simple tail recursive implementation of a effect runner. It keeps track of the remaining elements in the stack by using a list, and it performs some operation. It does not do any error handling, but we already considered that this is a very simple implementation. We don't need to worry about error handling for now. So now if we look at our complete code base, we have three functions. We have a read from console, a write to console, and a program that is composed from these two functions. And at the end of the world, we run the program. So 90% of our code is composed of pure referentially transparent code base, and only at the end of the world, we execute the program. Now, this is very important to understand that we did all this because we wanted to achieve referential transparency, and referential transparency guarantees us an ease of making our code bases easier to look at, not only in terms of refactoring, but also in terms of adapting to new use cases. Now we had to look at the effect type and we designed a new effect type for ourselves, but we don't need to do that actually. There are some awesome effect libraries available in the open source. We have Monix Task, we have Cats effects, and we have Zio. They all have their pros and some might say their cons. I'm not going to go into details of which one you should use. Your code base might have different requirements, and based on that you could choose. If you're already suppose dependent on cats, then you could as well start using cats effects. But each of them has its own use case. Each of them have their different FFIs, but the core logic is the same as what we discussed in our effect type. And I think that is what I wanted to talk about. That completes my session. Are there any questions?
No, any questions? No? Okay, then thank you very much, Ayush, for your presentation.